Big hand to all of you because it's nice to see this big crowd here. Capiche is very supporting to Foo Café because we want a forum for developers and other tech-savvy people to be able to discuss and attend to these kinds of event. So we are sponsoring this event as well as we are sponsoring all the work of Foo Café. And today it's going to be extra exciting because it's data science. That's what we do at Capiche. We do data science about clinical data from clinical studies. And we have just started to test R and Python in our applications. So warm hand to Rasmus, who will be the speaker tonight.
Yes. All right. Thank you, everybody, for being here. It's so nice to see so many people in the same space. Also a little bit scary, but I think it's going to be okay. So we're here to talk about 3 strategies to tackle big data. I'm Rasmus Bååth. I'm a data scientist at Castle. And I don't know if you remember big data, but it used to be like big around 2015. It was like kind of a buzzword around 2015, but not so anymore, I think. So around 2015, what people were talking about when they were talking about big data was kind of these large, these large data sets that companies like Facebook and Google were amassing, where you had all this data from all these users that you can analyze and do all kinds of amazing things with people are thinking. But that was in 2005, and if we look at the trend for like the Google Trends, it looks something like this maybe. So this is around 2005, 2006, 2015. This is when kind of big data peaked, and then now it's less of a buzzword, I think. It was kind of followed by, I think, deep learning somewhere here, and then AI here, and actually I'm not sure what the latest buzzword really is. Also, if you look at Stack Overflow questions, it kind of also peaked somewhere around 2016. So if you look at this, it looks like big data is not really a thing anymore. It might not be a buzzword anymore, but it's definitely still around. It's definitely still annoying to get big data. And you can see that if you look at some other Stack Overflow charts for some of the big data tools we're going to talk about today. So here we have the chart for PySpark. Spark, it's a big data tool, and it's just trending upwards. Same thing for some of the big data warehouses like Snowflake and BigQuery. It's also trending upwards. So even though the buzzword big data is dead, I think big data as a problem that you need to solve is very much alive. You'll also see this if you look at like ads on LinkedIn. Big data skills are very much in demand right now. So we're going to talk about 3 strategies to tackle big data. We're going to talk about a strategy I call use a local database, and we're going to look at a specific database called duckDB. We're going to look at using a computational engine, whatever that is. And here, a very common choice is Spark. And finally, we're going to look at using a data warehouse to manage and process and deal with big data. And we're going to look at a warehouse called a warehouse called Snowflake. But why do we need strategies to handle big data? Well, if you look at this chart here, it goes from 2000 to 2020. Do you know what it shows? It shows how annoying it is to handle how annoying big data is the first time you encounter it. It's super annoying. It's equally annoying over time. And it's annoying because suddenly when you get big data, you can't use your normal toolbox. Like the data doesn't fit in memory. You can't use R and the tidyverse, and you can't use pandas because they require that all the data fit in memory for you to be able to compute on it. So suddenly, all the years you spent learning these tools are like, what do I do now? Sure, there are many other tools to handle big data, but there are like too many of them, right? Which one should you choose? It's not clear, and whichever you're gonna choose, it's likely gonna be slow and expensive anyway. So that's why big data is kind of annoying. Like if you Google picture search big data, it's going to look like this, right? It's like big blue balls of promise, it's going to be amazing. But honestly, as a data scientist and analyst, big data is more like this. Like it's just annoying, it doesn't work, it crashes, and you have to wait all the time. So that's why you need strategies to handle this. One thing we haven't mentioned is like, what is big data? Sure, it's a lot of data, but how big should it be? Is this big data? Well, I think in the 80s this was big data. Like in the 80s, if you have data that you needed to fit on 2 floppy disks, then you had a problem because, like, of course, you didn't have a hard drive; you just had a floppy drive. So now you need 2 floppy drives to analyze your data. Like that's big data, but not anymore. So I think a good definition of big data is data that's so big it doesn't fit in the working RAM memory of your computer, and that's of course is a moving target. So if you look at the average amount of working memory since 2000, it kind of starts around 1 gigabyte here, 4 gigabytes around 2013. So right now, maybe big data is somewhere around 8 gigabytes, but often you need to process it and maybe make a copy of it. So maybe around 4 to 8 gigabytes. That's where I think you can start talking about big data. But it depends on on the laptop you have. Yeah, this is how big data looks on your laptop. Like everything is going well, and then you load it into memory, and then suddenly nothing is working anymore. So that's why you need strategies to handle this. And except for the problem with it having to fit in memory, there are 2 other problems with big data that I think you need to be aware of. Yeah, you want it to fit in memory, but since it's large, you also ideally want to process it in parallel, because like if you only use one single core to process it, it's going to take a long time because it's big. So like you also ideally want to process it in parallel, like, and that's kind of a separate problem for the memory problem. A third problem that might not be completely obvious is that it needs to be fresh and up to date. And that's connected to, like, there's a reason why you have big data. Normally you have big data because there's some kind of long running process. Maybe you have a website and it continuously outputs data that get appended and eventually it gets big. So often when you have a big data problem, you also have a problem with that the data is continually updated, and you ideally want to be working with the latest version of it. It's very rare, I think, to have a big data problem where you can put all the data on a hard drive and then that's it. Then you can analyze that hard drive for several years. That's usually not how big data works. It needs to be the latest version always. And R and Python doesn't really help you with any of this. Like the data have to fit in memory, like working memory. R and Python are by default like single core. And when it comes to the freshness, getting the data up to date, like you have to download the data again. I guess that's how you keep it fresh, but it doesn't help you in any other way. So here are the 3 strategies we're going to talk about. But why do we need strategies like right now? Well, I guess we need to do something with these strategies. So let's find a data set and let's have a simple problem that we want to solve. I found a dataset on Kaggle. It's called the Spotify charts dataset. It's 25 million rows of Spotify charts. It's 3 gigabyte large, a CSV file. So it's not really big data. Like maybe it's big data in 2011, but I think for our purposes here and now, I think it's big enough. So it's basically 25 million rows of this. It's like daily or bi-daily logs of all the top 200 Spotify lists for many different regions, and also a top 50 viral list that I don't know what it is. So you have like the name of the song, the artist of the song, the date the top list was recorded, and the rank of that song on that date, and then also what country or region that top list was in, and then some extra metadata. And there are many different questions you can ask about this data, but we're going to just ask one single question to make it easy. We're going to want to know which artists have spent the most time on the Swedish top 200 chart. That's the question for today. And it's kind of easy to answer that in R and Python. So let's start with that and see how that could look. So now you have to choose your poison. Here is going to be the R code if you like R. Here's going to be the Python code if you like Python. Well, let's load in some libraries. We want the tidyverse if you do R maybe, and pandas if you do Python. let's read in the data. It's big now, so let's only read in like the first 100,000 rows. That's a really small subset of this data. And then it's always good to take a look at it just to see that it looks all right. I didn't do a printout of this now, but this is what you normally want to do. Okay, so we want to take our chart data, and we want to look at only the top 200 lists. That's kind of a category of lists for Spotify, and only in Sweden. Did it go? No, it's back. We want to group by artist. And then for each artist, we want to know on how many distinct or unique separate states did that artist appear on a Swedish top 200 list. Like an artist maybe can have 2 songs at the same time, and then we only want to count that one time. So we just count the unique dates that we've seen that artist. And just for fun, we're also going to count the unique number of songs that artists have in total. And then we want to have the most popular artists, so we arrange it in descending order from most popular, most common occurring to least common occurring, and we take the top 10. So this is R and this is Python, and I also think it's fun that they actually look quite similar. And actually, let's actually try this out right now, just to see how it looks. So this is actually RStudio, and it's going to be a little bit of an experiment because I'm going to run a file here that mixes R and Python code, which you can do, which I think is super cool. But it has crashed at least twice when I've tried this specific document, but it's going to be fine. You can just restart it. So now I'm just going to run the code I showed you. We're going to import pandas. We're going to take a look at the data. Okay, we have a couple of songs here, some columns that were not shown, and send some metadata. And now we're going to look at the top 10 artists. But since this is only from a really small subset of the whole data set, we get some weird artists that I've never heard of. Arizona have been on the top list 8 times. Does anybody know Arizona? No? Okay, I guess not that popular. And in R, it's the same data. Load in the data, or it's the same code. Load in the code. We get a little bit of a nicer printout here because it is run in R after all, and we get the same list. All right, I verified that the R and Python code works, but that doesn't really help us because we only ran it on a small subset and we have big data, so we need a big data tool. So let's do the first strategy, use a local database. So what is this strategy? Well, the strategy is basically fire up a local database engine, and almost all database engines have the feature that they can compute on the data on disk directly rather than having it in memory. So that's why we want a database engine. So that means we're not bound by our working memory anymore. We're now bound by how much disk space we have, which, unless you have a lot of movies downloaded, is usually more than your working memory, right? But even though we have a separate database engine running, we're still going to interact with it from R and Python. There are many database engines that you could use for this. All are probably good. PostgreSQL is an old one. It's a little bit annoying to get started because it's a separate process. It's a little bit iffy to install. There's SQLite. It's a super useful database because it runs inside the R or Python, so it's very easy to get going with. But I want to highlight duckDB, which is a fairly new database. So what's duckDB? Well, it's a newish open source project created around 2018. This is how they describe themselves. It's kind of a mouthful. It's an embeddable in-process, column-oriented SQL OLAP. I don't know how. Do you know how to pronounce this word? Anybody? Okay, just say that. That's smart. Yeah, that's probably how you do it. Yeah. So what does this mean? Well, it's embeddable in process. That means it runs in Python and R. It's not like a separate program you have to run. So that's good. It's easy. It's column-oriented SQL. So that column-oriented just means it's good for analytics in this case. And SQL means you program it using SQL, like this old 70s structured query language that most table-based databases use. It's OLAP. That just means it's made to do analytics rather than made to do transactions, which normal production databases are kind of made for. And it's a relational database management system, which again just says it's a database for tables, which is what we have. So that sounds good. And yeah, it's really easy to install and runs inside R and Python. But you cannot, it doesn't run R and Python, so you have to program it in SQL. Can I get a show of hand? How many here have some experience with SQL? Yeah, I mean, it's an old language. If you're in tech, like sooner or later, you're going to be afflicted by SQL. I just want to, for those here that haven't looked at SQL, I just want to take these two small programs and make the comparable SQL version here. And it's also fun because you're going to see that they are very similar. So from charts, where the record is from the top 200 list and in Sweden, we're going to group by artist. And select here is a little bit of a weird statement because it both selects what columns we want to see, but it also does computation here. So we want to select the artist column, but we also want to count the distinct dates and call that end date, and count the distinct titles and call that end song per artist. And then we want to order by dates descending and just take the top 10. Is there something wrong with this SQL statement? Can somebody see something that's off? Select first. Yes, it's in the wrong order. So like this is the natural order you would write it, but for some reasons in SQL they decided that select has to be on top all the time, which is completely weird, but that's where we are. So this is the SQL program that embodies these two programs. All right, armed with that SQL statement, let's actually run some big data analysis. So we're gonna, I've already installed duckDB, that's just a pip install. We're gonna connect to this database, which is just gonna be a file on disk. And then we need to load in the CSV file. And that's the statement here. So now when we've created this connection, we can use the con.execute and run any SQL code as a string. And this is how you read in a CSV file in duckDB. So you create a new table, call it charts, and create it as select everything from read this CSV file, please. And that's if the CSV file is in the right format, this is just automatically going to read in this CSV file. So I think this is kind of low effort for a database to read in a CSV file. This takes like 1 minute, so I've already done that. So we can take the next step and just look at some data. So again, I'm executing an SQL statement, select everything from charts, but only 10 rows, please. And then you have to do this fetch data frame to just get the data out. And we see a couple of rows from this data set. And now, finally, we're going to execute this SQL statement that I showed you before. This is going to run on 3 gigabytes of data. It's going to run on all my cores. And it's going to calculate the 10 most popular Swedish artists. And there they are. So the most popular artist is Hovet, followed by Avicii, Ed Sheeran, Lali. At least I recognize some of these artists. I don't know if you do. Okay. And once we're finished, we're just going to close the connection, and that's it. I think for being big data, I think duckDB is fairly low effort. And for your R people out there, we're now going to do the same thing in R. Here we're going to use the DBI package, which is kind of an R package that just defines a couple of functions that can be used with almost any type of SQL database. So you have the kind of same interface to any type of database. So DB connect, for example, is a DBI function. So we're going to, again, connect to duckDB. And that's where it usually crashes. So I'm just going to start a new session and read in my settings. I haven't been able to figure out why it crashes there. But it has something to do with RStudio, not with duckDB. All right, we connect to the database. It's the same SQL statements as before, so I don't think I need to mention them. But now you use the db execute method to run an SQL statement like this that inserts data. And then when you have a query, you use the db get query instead, the connection object, and then the query you want to run. And yeah, it's the same query. Hopefully we'll get the same result. Yep, we do. It's Hovet on top and then Avicii, Edge Run, and so on. And let's close that down. All right, so that was duckDB. And duckDB is good in many ways. Like, it's super easy to install, it runs locally, and it also runs really well. Like, it uses the full capacity of your laptop, all the cores, your whole disk. It performs really well. And it's also actively developed. There's a lot of features added every month. However, you're stuck with standard SQL. Like, you have to write SQL, and also it's kind of standard SQL, so there's not that many fancy methods that you can use. And it runs locally only. So it's good if you want to do stuff on your laptop, but there's no easy cloud solution that can help you fire up like a huge machine to run this on. So yeah, there's no easy hosted option. And it's a fairly new project, so there's like regular breaking changes to duckDB. That's something to be aware of. If we compare it to R, I would say it kind of halfway solves the memory problem in that it uses all the memory on your laptop. But if your laptop is too weak, like the disk is too small, there's no hosted option that can help you out here. In the same way, it uses all the core on your laptop, but there's no hosted option that you can use to get a really beefy machine. It doesn't help with freshness at all. You still have to download the data manually and insert it into duckDB. Any questions on duckDB? Have anybody heard it before? Yeah, sorry.
I haven't heard it.
Yeah.
How does it compare to SQLite?
Yeah, so that's a very good question. Basically, duckDB is the analytics database that analytics analog to SQLite. So SQLite, like the use case there it's like a transactional database in that it's optimized for grabbing a single record quickly and being able to insert records quickly. It mostly runs on a single core if you have a single query. While duckDB, it's super if you want to insert a record or just grab a single record, it's going to be super slow. But it's really optimized for like running huge queries in parallel analytical queries. So that's basically the whole gist is we're SQLite, but for analytics. All right. Strategy 2, use a computational engine. So this strategy is basically fire up a local computational engine. So computational engine here is not a database per se, but some kind of framework or server or app that's tailor-made to run computational workloads. So you can fire it up locally and use all the data on disk, not only in memory. Or even more popular, you can fire up a remote computational engine on a really beefy machine. So for example, Amazon EMR, their most beefy machine that I've run a couple of times have 384 gigabytes of memory and 96 CPUs, and I think that's kind of beefy, right? It also costs like, I don't know, it's like $10 an hour or something like that. So it's also kind of expensive. But again, you still use R and Python to actually control this engine. Here there are also a couple of options. There's Dask, which is pretty cool. It's basically a Python-only engine that allows you to run what looks like a normal Panda statement, but distributed. It's pretty cool. There's Flink, which is more of a streaming framework, but can also be used to do any type of distributed computations. And then it's Spark, which we're going to look at today. And Spark is a pretty, relatively old for big data project. It was launched in 2012. And I think it's kind of the most popular computational engine around nowadays. They describe themselves as a unified analytics engine for large-scale data processing. Basically, it's like it's a program that runs analytical workloads. And and Spark does a lot. Like it's not only an SQL database, it does SQL, but it also have a lot of routines for machine learning. It does streaming. It kind of half-heartedly does graph computation. You can run custom Python function, but distributed. It does a lot of stuff. And it's possible to run locally, like on your machine. But it's very common to pay like a cloud service to do this for you. Amazon EMR is one of those, but Databricks I think is the most common because it was started by the people that actually made Spark. So, I just want to have anybody here used Spark? Do you like it? It's okay. That's also my feeling about Spark. Like it's okay, but how do you?
It gives you lots of opportunities.
Yeah.
Which you cannot do on your local machine.
Yeah. It gives you a lot of opportunities to crash Spark. Also, it's kind of fiddly. It's kind of fiddly, but I'm gonna try to run it on my own local machine anyway. Okay. So we're gonna run Spark. We're also gonna look a little bit about on how Spark code actually looks. So let's first run it in Python. Already here you can see there's a little bit more boilerplate going on, just even starting Spark. This is not half of the story. Like to just install Spark, it's like a separate program. You need to make sure you have the right Java version installed. Like it's kind of more involved than just installing like duckDB. But we're gonna run this. So this is gonna start a Spark as a separate process somewhere here on my laptop. It's probably gonna print out a lot of angry red code, but that's just info. For some reason it's red. And at the very end we get a little URL actually here. If we go to that URL, oppa. We actually go to the Spark job server, which actually is like a local server that shows all the stuff that you've been running in Spark so far, which is kind of cool. And here now is how you read in CSV files in data. So Spark has its own like domain specific language. It's not like pandas. It can do most of the things that pandas can do, but it's like have its own methods and functions and so on. So it's a little bit involved to learn that, but you will get a flavor of it here. So we're going to read in the data. And if you go to the Spark server, you can now see that it actually ran something. Here is how you look at the data, like the head of the data charts. We want to see 10 things, and then we want to show it. So that gives us a couple of rows to look at. The printout is not that nice because it wraps weirdly. And here is the Spark code to run to answer our question. I'm not going to go into much detail. You can see it's kind of similar to the SQL and the Python code, but it's not the same methods. So like from charts, we want to filter by these things, group by artist. Then we count distinct. It looks a little bit weird. We want to sort ascending false, that is the largest on top, and then look at the top 10. So basically you can do anything you can do in pandas, but you have to learn the Spark way of doing it. And if I now run this, Spark is going to do a lot of work. You can see that we now started a job here. And if I refresh, you can see that it's now running 25 different small jobs, 9 running. And if I go to executors, you can actually see that it's running currently 9 different tasks. So it's now running on all my cores, trying to be really, really busy. So Spark is really good at this. It runs everything distributed on all your cores all the time. And now we can see that it stopped, and hopefully then it finished. All right, here we have the same list again, Hovet, Avicii, and so on. So that's using Spark, using the PySpark kind of package. But Spark also have support for SQL. So if you already have the SQL query, like we have before, you can register the Spark data frame, and now you can use it by in SQL queries like this. So spark.sql, and then it's SQL as before. So here is again the SQL query we looked at before. It's going to calculate the same thing, and hopefully we get the same result. Spark is going to be busy again. I can feel my computer becoming warmer, which is good. But you did notice that this actually was slower than duckDB. I don't know if you noticed. So the thing is, like, Spark is really good at being extremely busy, but when it comes to like medium-sized big data, it's actually often quite slow. But then when it comes to really huge data, it's often quite fast, because then something like duckDB just doesn't really work. But Spark is slow on small data. All right, let's stop it. Okay, now we're going to do the same thing in R, and this is actually going to look different this time, because in R there are a couple of different packages you can use to interact with Spark. So there's the old Spark R package. We're not going to use that. We're going to use the Sparkler package instead. And the Sparkler package is pretty cool because it's basically a dplyr tidyverse implementation of Spark. So you can write what looks like normal tidyverse dplyr code, and it will translate that into Spark code. So with a little bit of luck, if you have a tidyverse dplyr pipeline, you can just directly use that. Another thing you see with Spark here that is one of the annoying things with Spark is that it's often very slow to start. Everything takes a long time. Also, if you use like something like Amazon EMR, which is a service to easily start a huge Spark instance, it still takes like 15 minutes just for that thing to start. So there's a lot of waiting time here, which is a little bit annoying. Actually, I'm not sure what Spark is doing right now. Let's see what it's still trying to connect to the local instance here. Let's try again. Okay, this is just taking too long. Maybe I can just show you the code instead. Well, I mean, okay, the code is actually not that exciting because it's exactly the same dplyr code I showed you before. But this is just gonna run and give us the same result that we've been looking at like 4 or 5 times now. But for some reason, Spark don't want to start. Let's just start a new session here. Okay, you've seen the tables, so you don't need to run it again. So let's go on here. So there are some good things with Spark, like you get it all. Like Spark, now we just looked at basically what you can do in SQL, but it has like machine learning routines, streaming, a lot of stuff. You can run it on your computer, you can run it hosted somewhere else. It connects to many different data sources. Like if you have it hosted, usually you can connect to everything that you have, say, on AWS or any data lake that you might have lying around. It's really good at connecting to many different data sources. There's a large community. It's a very common tool. So like if you have a problem, you'll probably find the answer on Stack Overflow. That's good. But if you want to program it, you either have to do it in SQL or like you have to learn the PySpark, all the new PySpark commands. So like it's a completely new API. It's a little bit annoying to learn that maybe. And even though you can run it locally and hosted, it's actually not necessarily easy to install and run locally. And hosted is usually fairly expensive and surprisingly fiddly, actually. Also, to actually make Spark run well, you have to set like a ton of different options. That's actually pretty hard. And as you've seen, it's fairly small on small data. It's fairly slow on small data. But since you can run it hosted, it gets a big check mark on memory. Like if you have more data than 386 gigabytes of RAM can handle, then maybe it's hard. But for most cases, that's going to be enough. Parallelism, it uses all the cores. That's great. And freshness is kind of okay. You have to do a lot of work yourself, but at least Spark can connect to basically every data source that you have. So we're a little bit, how we're doing on time. We have 10 minutes left, right? That's correct. Okay, then we're good on time. Okay, last and final strategy. This is the most big data strategy of them all. Use data warehouse. Okay, so now the third strategy is to use a cloud database engine that is purpose-built to handle big data workloads. Okay, that's basically the strategy, but still interact with it from R and Python. And I think there's actually basically only two options here. There's Google BigQuery and there's Snowflake. Amazon have an offering there, but I think these are basically the two options. At my work, where I work at Castle, we use Snowflake. So that's why we're going to look at Snowflake. But it's been really good. Like, I use it daily, and it's an amazing piece of cloud software. Like, it's super stable. It has never crashed. It handles any size of data. It's really amazing. They don't pay me to say this. Yeah, sorry.
Why on earth are you bringing data out of Snowflake? You can run SQL in Snowflake without having to move data anywhere.
Right, but you at the end you often want to get it into R and make a pretty plot, for example.
So you run stored procedures, so UDFs, and then you sort of get the results.
Yeah, or like you run SQL code in R, and that gives you like the smaller data set that you want to plot or analyze, or
Can you distribute SQL from R into Snowflake?
yeah, I'm gonna attempt to doing that very soon. We see how it goes. All right, so what's Snowflake? It's a commercial service. Like, it's not open source. It's like it's a software as a service thing, launched in 2014. They describe themselves as a cloud-based data storage and analytics service. I think that's pretty self-explanatory. It's a data warehouse, so you have to communicate it to or use SQL to program it, but it has a fairly advanced SQL dialect that can do quite a lot of things. Snowflake became like a thing because it was the first data warehouse to separate storage and computing. So that means that you can store a lot of data without having to pay for compute. Normally, back in the days, if you want to store a lot of data and you want to store some more data, you would have to buy a second computer, but that means you also had to buy like a second CPU, right? You couldn't just buy too many hard drives. You have to buy more computers and more hard drives, but Snowflake is separating these two things. So you can just store data, or you can just compute on data, but these are two different costs when you use Snowflake. So that's why they kind of became big. And as I say, it's like, this is truly petabyte scale. Snowflake can handle any size of data. And let me show you how it handles 3 gigabytes of data. So actually I cannot show you that yet, because Snowflake, like, it's a service, so you cannot just start using it like that. You have to sign up for like a Snowflake account, right? And you can also see you get $400 worth of free usage. That tells you that it's probably kind of expensive if they give you $400 for free, you know. And actually, you also probably need like a cloud provider, because you need to get the data into Snowflake somehow, and that you do that usually by kind of putting it in like S3 in AWS or something like that. So we have to sign up for that, and then we have to upload the CSV file to Amazon in order to get into Snowflake. So compared to duckDB, this requires much more work. But I've done that work, also my company has done that work. So I'm going to use Aaron works at my company. I'm going to use my company's instance of Snowflake. I think they can pay for that. All right. Let's scroll down here. All right. So now there's even more stuff we need to do just to get started. Like here, we're going to use SQL Alchemy. It's kind of a standard Python connector to many types of databases. But then we need to have all of these credentials just to connect here to Snowflake. So there's more boilerplate here. Hopefully this works. Alrighty, we are connected to a cloud database somewhere in the US. I don't know where. We're going to ask them to give us some rows now. So here I'm using actually pandas method called read SQL query, but that works really well for some reason with the Snowflake connector. So you give it the connector and then the SQL code, and you get out a pandas data frame. And in the same way, we can run our SQL query that answers the what are the top Swedish artists. Okay, let's try it. Did you see how fast that was? Like that's like 3 gigabytes of data on another, like in the US, and it like returned instantly. Like that's the thing with Snowflake, is so fast. That's, I think, is kind of amazing. It's the same list we've seen before. Let's get rid of this. In R, it's basically the same, or it's actually exactly the same, because we're going to use the DBI interface. So it's going to be exactly the same code as in duckDB. But yeah, let's just do it anyway. So it's going to be db get query again. It's the same thing. It's equally fast. I think it's quite amazing. So that was Snowflake. It worked. Okay, there's a lot of good things with Snowflake. Like it's a really advanced SQL engine. It's fully hosted, and for all the things it does, it's like fairly low maintenance. It's truly petabyte scale. You can handle any type of big data with it. It works with many cloud service providers, Azure, Google Big Cloud, AWS. It has a nice web interface that I haven't shown you. So you can write SQL queries directly in the web interface, and it really connects to anything and everything. So it's really to have the data up to date. So Snowflake can stream in data from like Kafka and wherever you have it. But like negatives, like it's still SQL. So if you're used to having the power of pandas or R, like you're going to be limited to what you can express in SQL. There's no way to run this locally. Like if like the vendor lock-in is 100% here. If you have a lot of reports with Snowflake style SQL and you stop your Snowflake subscription, like you cannot run that anymore. So like the vendor lock-in is 100% here. It's kind of corporate scale, so a lot of things costs money. And like, sure, it works with many cloud service providers, but like, do you really want to have a cloud service provider? Is that something you've been longing for? Like, I guess you need a cloud service provider now. Like, there's a lot of stuff that you need to set up just to get this going. And it can cost quite a lot of money compared to doing it on your own laptop. Yeah.
You evaluated Snowpark yet?
What is Snowpark?
Snowpark is an API that is very similar to using Spark. That's been launched and proven.
No, I have not used it. So you would say that's kind of a computational engine.
Well, as many youngsters like you don't like SQL, they're now providing something that's more like a programming language.
All right. No, I haven't tried that. Though I would say I actually like SQL quite a lot. Maybe more than I should. Yeah. All right. So I mean, Snowflake, roughly like Spark, like memory is not a problem. If you have the data there, you can compute on it. Super parallel, super quick if you pay for it. And freshness, like sure, you have to stop stuff yourself, but if you do that, then it can connect to anything and everything. So this kind of summarizes the three different strategies and kind of where I think they are good and bad. And in general, if you like have big data, I think a good meta strategy is kind of to start from the top here. Like, can you compute on this data using duckDB? Then that's the easiest option. Then do that, please. That's good. If not, maybe prototype in Spark, and if you really need to, you can fire up like a hosted service where you can compute on it, like using the full power of Amazon, for example. And if you have truly large data, then I think it's really hard to avoid using a data warehouse. Like that's really where you want to go if you have huge, humongous data. But have you noticed a similarity between all these approaches?
Well, Snowflake allows you to sort of put in terabytes of stuff.
Yeah.
You start with an extra small warehouse, and if you need, you can put in your big, whatever it is in ABS.
that's true. But I mean, is there a specific query language that all of these methods allow you to use, or? Yeah, they're all relational, and you can all use SQL on all of this. And I think when you're doing big data, it's really hard to avoid SQL. Like for some reason, this weird language from like the 70s is the thing you have to use nowadays to deal with big data. So if you haven't used SQL, I think you will have to at one point, even if you don't want to. But actually, you can do quite amazing things in SQL if you just if you want to. All right. So this before we have the pizza, there's just one more mystery, and that's the mystery of journey. I don't know if you saw journey in the top 10 list we calculated before. I can show you. So here we have journey. They're on spot 6 here, and like all these other artists, like the Hovet, they have like 46 different songs, and Avicii has 52 different songs, but Journey just have one single song. Like that's really weird. So let's figure out which song that is. If you know it, don't tell me. So from our data warehouse in US, we're gonna select all rows where the artist is Journey. Dun, 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 dun. And this time it was actually quite slow. That's a little weird. Okay, let's restart the session. Okay. Does anybody know what song it is? No? All right. It's Don't Stop Believing. For some reason, it's an evergreen song. So let's put that on, and let's have some pizza. All right. Right, that was 3 strategies to tackle big data in Python and R. So this has been a meetup from Data Science Malmö together with Foo Café. We have some more stuff coming up, so please search for Data Science Malmö and join these 2 events if you feel like it. Right, thanks.